Good morning, students. In my last lecture, we discussed about basically the scheduling module of the operating system, in which we studied that in order to schedule processes to get CPU, basically we need to have some scheduling algorithms. So before designing any scheduling algorithm, we discussed that we need to understand basically the behavior of the process. Behavior or the nature of the process means that whether that particular process is a CPU bound process or an input output bound process. So because depends on that, we need to schedule a particular process. Then the second thing which we discussed is basically the situations in which we need to schedule a particular process. We discussed about the different situations also, like whenever a process switches from running to waiting state, then also we need to schedule a particular process. Whenever a particular process moves from running to ready state, then also we need to schedule a particular process. Similarly, if a process moves from waiting state to ready state, then also we need to schedule a particular process. And if suppose a process terminates and exits from the system, then again we need to schedule some another process from the ready queue. And the next thing which we discussed is basically the dispatcher, that it is the responsibility of the scheduler to schedule a particular process, but the actual dispatching of the processes, or you can say that actual allocation of the CPU to the processes, is done by basically the dispatcher. So we discussed about the dispatcher also. And then we considered, or we discussed about the different scheduling criteria, which basically helps us to improve the efficiency of a particular scheduling algorithm. So those features are basically the fairness, CPU utilization, balanced utilization, throughput, turnaround time, waiting time, and the response time. So these are the different scheduling criteria, and on the basis of basic purpose of the CPU scheduling algorithm is that it should always tend to maximize the fairness, CPU utilization, balance utilization, and throughput, and we need to minimize basically the turnaround time, the waiting time, and the response time whenever we are designing any scheduling algorithms. So in this video we are going to discuss the different types of scheduling algorithms, and we will study the different scheduling algorithms also. So the first type of scheduling algorithm is basically the non-preemptive scheduling algorithms. In non-preemptive scheduling algorithms, what happens basically, as once the CPU is allocated to a particular process, that it cannot be taken back from the process until the process voluntarily releases it, or the process finishes its task and terminates. It means that whenever we allocate a particular if we allocate a CPU to a particular process, then we cannot forcibly take it back from that particular process. It means that the scheduler can schedule the another process only if the process enters into the waiting state or terminates. Waiting state means if suppose it enters into for basically the input output task. So whenever it enters to the input output task, then it automatically enters into the waiting state. Then we can schedule some another process, and whenever a particular process completes its task and terminates, then only we can you can say that we can allocate CPU to some other process. Now in both the cases, the scheduler allocates CPU to the process from the ready queue, and it is sometimes we call it basically the cooperative or the voluntarily scheduling algorithms. So they are actually from your syllabus we need to study only two non-preemptive scheduling algorithm. One is the first come first serve, and the another one is the shortest job first. Now the next scheduling algorithm is basically the preemptive scheduling algorithm. So in the preemptive scheduling algorithm, the CPU can be forcibly taken back from the currently running processes before its completion and allocated to some other processes. The preempted process is taken back into the ready queue and resumes its execution when it's scheduled again, and a process may be scheduled many times before its completion. So basically this is your preemptive scheduling algorithm, in which basically we can forcibly take the CPU from a particular currently running process and assign it to some other process. So what are the situations in which we can actually, a scheduler can preempt a CPU from a particular process? So one is basically that whenever an interrupt occurs that causes a currently running process to switch to the ready state. suddenly if suppose any interrupt occurs, then in that case basically the particular currently running process it will move to the ready state, and the moment it moves to the ready state we can schedule the another process. And similarly, whenever we will see about the processes with higher priority comes, what happens, that whenever a process with higher priority comes, then in that case also basically what happens, the CPU is taken from that particular process and assigned to that higher priority process. So this is another basically the situation in which a particular process, the CPU can be forcibly taken back from a particular process, Now we are going to start basically the non-preemptive scheduling algorithms. So in non-preemptive scheduling algorithms, from your syllabus we just have to study two algorithms. One is called the first come first serve, and the another one is called as the shortest job first. So what happens in the first come first serve scheduling algorithm? So it is the most simplest scheduling algorithm, and the processes are executed in the order of their arrival in the ready queue, which means that the process that enters the ready queue gets the CPU first, and since it is a non-preemptive scheduling algorithm, once the CPU is allocated to the process, it retains the control of the process until it voluntarily releases it. So this is called as the first come first serve. The moment the first process comes to the ready queue, the CPU is assigned to that particular process, and when that particular process is executing, the other processes can come and stand in a queue, and whenever the first process gets completed, the next process in the queue gets the CPU. Now how to implement this? So the implementation of the ready queue is managed as a FIFO queue, first in first out queue. When the first process enters the ready queue, it immediately gets the CPU and start executing. Meanwhile, the other processes enters the system and are added to the end of the queue by inserting their process control blocks in the queue. And when the currently running process completes its task, the CPU is allocated to the other process in the forefront of the PCB. See, by mistake it is written PBC, it's actually PCB of the previous process, and so previous process is basically deleted. So what happens basically for the first come first serve, when a particular process gets the CPU to start executing, then the other process comes, their process control blocks are stored in basically the queue. The moment this process completes its task, the other process from the queue is assigned, the other process gets the CPU and it starts executing. And so this is basically called as the first come first serve. The advantage of this is basically that it is easy to implement, since the processes are added at the queue and removed from the front of the queue, and it is well suited for the batch system, where the longer time period for each processes are acceptable. Whenever we are having longer time period for a particular process to execute, then it is always considered to be the best scheduling algorithm. And one of the other disadvantage is that the average waiting time is not minimal, and thus is recommended where performance is the major issue. See, in the next video I will give you one example. From that example you will see that if we assign processes on the basis of first come first serve, and or otherwise if we assign processes on the basis of shortest job first, or you can say the minimum CPU burst time, then you will see that automatically you will see that the turnaround time and the waiting time is drastically decreased in case of the processes when we schedule a processes with minimum CPU burst time. So you can say that the waiting time and the turnaround time is not that good in first come first serve algorithm compared to the shortest job first algorithm. And the second one is basically that it is not suitable for time sharing system. That if suppose you have multiple processes and all processes should get equal share of time, during that time period, during that kind of situation we cannot allocate basically whenever a particular process is executing, we cannot give equal time share to other processes. For in the situations in which time sharing is important, in those situations also we cannot actually use first come first serve scheduling algorithm. Now the next is basically the shortest job first scheduling algorithm. In the next video, while explaining the example of the first come first serve, I will show you the turnaround time, the difference between the turnaround time and waiting time in shortest job first, and same problem in basically the first come first serve. You can understand that basically both the turnaround time and the waiting time is minimum in shortest job first compared to that of first come first serve. Now what is basically the shortest job first scheduling algorithm? It is again a non-preemptive scheduling algorithm that schedules the processes on the basis of their CPU burst time requirement. At any point of time, the process with the minimum CPU burst is scheduled first. In case two processes have the same CPU burst time, then they will schedule on the basis of their first come first serve. So the processes are scheduled on the basis of minimum processing time, and the CPU is initially allocated to a process which is present in the ready queue. Spelling is mistake here, it's ready queue, okay, and later the processes with minimum CPU burst time is scheduled, and subsequently the other processes are added in the queue on the basis of the minimum processing time. So it means that in shortest job first, we need to allocate CPU to those processes having the minimum CPU burst time or minimum processing time. Now what is the advantage of shortest job first? As we discussed, that the main thing is basically in the shortest job first, the average waiting time and the turnaround time is definitely minimal as compared to other algorithm. As we discussed while studying the scheduling criteria, that the turnaround time, waiting time, we need to minimize these two parameters of the scheduling criteria in order to derive in order to compile you can say a very good efficient scheduling algorithm. We need to minimize the waiting time and the turnaround time. So therefore this is the advantage which we get from the shortest job for scheduling algorithm. And the next is the disadvantage is basically that it is difficult to implement, since it requires to know the CPU burst time in advance, which is actually practically it's difficult to do that. So that is the one disadvantage. And the another one is that if since we are executing basically the processes with minimum CPU burst time, so the processes having the maximum CPU burst time is basically is starved. Starvation is basically, we call it starved means basically they are maybe there is possibility that they will never get the CPU. So that starvation part we will discuss whenever we will study the deadlock unit. So this much is done for this video, and in the next video I am going to upload basically the two examples of both the examples of the shortest job first and the first come first serve, and then we can have a comparative analysis between the waiting time and the turnaround time of these two scheduling algorithms, and then we can move to basically the preemptive scheduling algorithms. Thank you.